Good morning. We will start with the chapter coordination compounds. In this video, we'll discuss the introduction of coordination compounds and some ligands, types of ligands. So, starting with the coordination compounds. What is a coordination compound? A coordination compound contains a central metal atom or ion surrounded by a number of positively charged ions or neutral molecules. These ions or molecules rebonded to the metal atom or ion by a coordinate bond. So basically, what is a coordination compound? It basic coordination compounds contains first of all a coordinate bond. So in a coordination compound, there is a metal and there are ligands. Ligands are electron rich and metal is electron deficient. Okay, metal ion is present there with some positive charge. So ligand, what it does, it donates both of its electron. Ligand contains a lone pair of electron or it contains a negative charge. It donates both the electrons to the metal, forming a coordinate bond. They are joined via a coordinate bond. Coordinate. So, for example, here you can see K4 FeCN6. So, you must be thinking that why are we writing a coordination compound in this fashion? So, in a coordination compound, you will see in further video that a coordination compound consists of two spheres. One is inner sphere, that is this one, in a coordination sphere. So, and this is a counter ion. Counter ion. Here, the coordinate ion. This square bracket represents the coordinate ion. Okay, so the iron here with 6Cn is forming a coordinate ion which has a potassium as its counter ion. So this is how this thing looks like. It has 4 as a counter ion. Okay. So they basically, what is the quality of these coordination compounds is that they do not they do not dissolve in water. For example, if you take ionic compounds like sodium chloride when added to water, what it will give you? It will give you sodium ions and chloride ions. But when you add a coordination compound containing a counter ion and a coordinate ion, what will you get? If I am adding like NaCl is NaCl is an ionic compound. If I am adding NaCl to water, I'll get Na positive ions and Cl minus ions because it is an ionic compound and ionic compounds get dissociated in water. But for the coordination compound like K4 FeCN6, when I am adding water to this, what I'll get 4 K plus ions plus one coordination ion. The formulation inside this square bracket, it does not dissociate. So you need to understand this that this what is it is the difference basically that the coordination compounds the coordinate ion do not dissociate in water. When you add a coordination compound to a water, there will be only the dissociation uh, of the counter ion, not the coordination sphere. So we'll understand these terms coordination sphere and counter ion in the further part of this video. Coming to the double salts. What are double salts? Double salts are those salts when two salts in stoichiometric ratio are crystallized together, form their saturated solution. They are called double salts. For example, If you can see Mohr salt is basically iron sulfate, ammonium sulfate, dot 6H2O. There are two salts here, iron sulfate and ammonium sulfate. And when these both are crystallized in stoichiometric ratio and generate a saturated solution, and in whole generates a Mohr salt. It is basically an ionic salt, but as I said in the previous slide, when you add water to an ionic salt, what it will do, it will simply dissociate. So in water, what will you get? You get one this Fe2, you will get sulfate from that, iron sulfate, you will get two ammonium ions, and you will get two sulfate, the sulfate from this. So in total, this will be the dissociation when you add water to a double salt or ionic salt, similarly to an ionic salt. Coming to the third term, that is a coordination entity. Coordination entity is a entity that constitutes a central atom, metal atom, ion bonded to a fixed number of ions and molecules. I told you that in K4FeCN6, in K4FeCN6, basically a coordination entity is iron bounded with six cyanide ions. So this part of this part, the one in the square bracket, is basically the coordination entity for this molecule having a charge of 4 minus. Okay. So here, as you can see, I should have written below. In this K4FeCN6, the formulation inside the square bracket represents a coordination entity. Okay, this one. This one. Coming to this coordination entity, we have understood that a coordination entity is that part of the coordination compound which is inside this square brackets. Okay, and it does not dissociate when added to water. So inside this coordination entity, there is a central atom. Central atom in a coordination entity is the atom or ion to which fixed number of ions or groups are bound in a definite geometrical arrangement around it. It is called the central atom or ion. As you have seen, I have drawn two times this coordination entity, and each time what I did, I drew a iron atom, and around that, in a octahedral fashion, I added the cyanide ions. So that means a proper geometrical arrangement is there around the central atom. So here the central atom for this coordination entity is this iron. So iron 2 plus is the central entity. Why iron 2 plus? If the whole entity contains a 4 minus charge, here you can see 4 minus. So what will be the oxidation state of this iron? X minus plus cyanide has a oxidation state of -1 into 6 such molecules with the overall negative charge of -4. So X minus 6 gives -4. So overall X will have a charge of +2. That's how the iron over in here has a charge of +2. Coming to the second part of a coordination entity, that is the ligands. Here the ligands bound to the central atom is cyanide. So a molecule or ion or group that is bonded to the metal atom or ion in a complex or coordination compound by a coordinate bond is called a ligand. It may be neutral, it may be positively charged, or it may be negatively charged. Examples for neutral ligands are like water, ammonia. Positively charged could be NO plus, or negatively charged could be Cl minus. Okay. Coming to the other terms like donor atoms. A donor atom of a ligand attached directly to the metal is called a donor atom. Till now, you understood that ligand donates its lone pair to the metal, either a lone pair or some negative charge. It donates to the metal via coordinate bond. So the atom of the ligand, a ligand could be Cl minus H2O. Okay. In case of Cl minus, the Cl is a single atom, so it will donate. In case of H2O, the lone pair is present on oxygen. So oxygen over here is the donor atom that will donate its electron to the metal. Hydrogen is not the donor atom. Similarly, ammonia, a lone pair is present over nitrogen, so it will donate its electron to metal. For example, in K for FeCN6, Cn is the donor atom. Cn, K for FeCN6, if you see, uh, so in case of K for FeCN6, as I draw Cn. So over here, carbon and nitrogen has three double bonds. So over here, carbon has one negative charge. So this negative charge will be donated. So the donor atom over here is carbon. Okay. So donor atom is the atom which is directly linked to the metal. It's called the donor atom. Coming to the next term, that is coordination number. Coordination number of a metal ion in a complex can be defined as the number of ligand donor atoms to which the metal is directly bonded. So number of donor atoms. For example, in K for FeCN6 you take, there are six cyanide molecules attached to the iron. So the coordination number for this iron will be 6. Six cyanide molecules are attached in octahedral fashion. So the coordination number for this iron atom is 6. Okay. Now let me give you one another example. Like if iron is attached to uh, this what you can say, ethylene diamine. You know the ethylene diamine is also a ligand. So it is basically CH2 CH2 NH2 NH2. So if I am writing in this formulation that, for example, some cobalt, ethylene diamine can be in short written as En. So En3. What will be the coordination? What is the coordination number of this cobalt? How will you define? Even if it is written 3, but overall, what will be it will be like, that is one NH2 over here, one NH2 over here. This is one molecule. Another NH2 over here, CH2, NH2 over here. So this is two molecules of ethylene diamine, and third molecule I am trying right now, that NH2. So this is the, so what is the coordination? Even if you see this kind of formulation, then you might get confused. Like it is not the coordination 3. Coordination number is not equal to the number of ligands. So if we consider the number of ligands, then number of ligands here is 3. But the coordination number is not 3. Coordination number is rather 6. Because coordination number is actually the number of donor atoms attached. But if a ligand has 2 donor atoms or 3 donor atoms, then it doesn't mean that coordination number will be equal to the number of ligands. Coordination number is always equal to the number of donor atoms attached to the metal. Coming to the next term, that is a coordination sphere. A coordination sphere can be defined as a central atom or ion, and the ligands attached to it uh, are enclosed in a square bracket. and are collectively termed as coordination sphere. In the first slide only, I told you that in K4 FECN6, the formulation inside the square bracket, that is FECN6, this is called a coordination sphere, and this will not dissociate in water. Coming to the next term, that is counter ions. In a coordination compound, the ions present outside the coordination sphere are called counter ions. In K4FeCN6, if you consider, the part inside the square bracket is called coordination sphere and the part outside the coordination sphere is called counter ions. So how many counter ions are there? Four K plus counter ion is there. What is the charge on this coordination sphere? It is FeCN6 4 minus. Now one more thing. Tell me what is the oxidation state of this iron? I have already shown you, considering the oxidation state as X minus plus 6 of the cyanide ion. Cyanide has a charge of -1. So minus 4 x minus 6 comes out to be -4, x is equal to +2. That is, iron has a charge of +2. Coordination polyhedron. A coordination polyhedron can be defined as the special arrangement of the ligands or atoms which are directly attached to the central atom or ion. Defines the coordination polyhedron about the central atom. Basically, coordination polyhedron is a arrangement of the ligands. Arrangement of ligands. In the case of K4 FeCN6, FeCN6, K4 FeCN6, the spectral arrangement of the cyanide ions around iron is octahedral. That is the coordination polyhedron here. The most common coordination polyhedra are octahedral, square planar, and tetrahedral. So, in most of the times, you will see that the coordination compounds are generally coordinated with 4 ligands or 6 ligands. And in the case of 6 ligands, there is a possibility for the formation of an octahedral complex. Octahedral generally coordination compounds are of two types, like they could be octahedral or they could be tetrahedral. Tetrahedral in the sense, octahedral means they will be having 6 ligands and those 6 ligands will be joined in the form of octahedral fashion, and if they have 4 ligands they could be either tetrahedral or square planar. We'll see how we'll define whether the coordination complex having 4 ligands is a tetrahedral or square planar. We see that in further slides, so don't worry. Generally, just want to tell you that coordination compounds are generally 6 coordinated or 4 coordinated. For example, till now I was just telling one example, that is K for FeCN6, so that you can easily like understand with one example only all the terms related. But if, for example, if you consider this PtCl4, in case of PtCl4, how many ligands are attached? In case of PtCl4, there are 4 of this scleride ions. That means it has a 4 coordination number is equal to 4. Coordination number 4 could be either square planar or tetrahedral. So similarly, nickel carbonyl NiCO4 tetracarbonyl, it contains 4 ligands. So how we'll discuss that, how these two having 4 ligand each, one of them is square planar and one of them is tetrahedral. We'll discuss these in further slides, but for now just remember that coordination compounds are either octahedral, either coordinated with 6 ligands or either coordinated with 4 ligands. If are coordinated with 4 ligands, then it could be a square planar or a tetrahedron. Coming to the second term, charge on the complex sign. The charge on the complex sign is equal to the algebraic sum of charge on the ligands or the coordinated to the ligands coordinated to the metal ion. I have already shown you example of this. That is K4FeCN6. Let us take some other example. Okay. Here, as I told you, that FeCN6 charge on the complex ion. Complex ion is this one. -4. Charge on this ion, you have already calculated x minus 6, minus 4, x is equal to plus 2. Similarly, in the previous slide, you see that PtCl4. Okay, this was the charge. So let's suppose it is K2PtCl4. What is the charge on the complex ion? Charge on the complex ion is PtCl4 2 minus. This 2 goes over here and this 1 goes over here. We know this cross thing we did in earlier classes as well, that PtCl4 2 minus. This 2 minus is the charge of the complex ion. And how we'll define the oxidation state of this platinum? X minus 4 minus 2, x minus x is equal to minus 2 plus 4, x is equal to plus 2. Okay. Coming to the denticity. Denticity, till now we were talking about ligands, their coordination number, counter ions, and etc. Denticity is defined as a number of ligands or atoms linking ligands, ligating ligands, or you can say linking atoms present in the ligand. I told you that coordination number is equal to the number of donor atoms attached. In ethylene diamine, okay, number of ligating elements or linkage elements are 2. Okay, this nitrogen will bind and this nitrogen both will bind to the metal. Okay, in this one ligand there is 2 donor atoms bind, so this is a bidentate ligand. A bidentate ligand is the one that is attaching to the metal via 2 coordinating sites. A monodentate or unidentate ligands, we'll discuss, we're discussing about the denticity. Denticity, we define ligands on the basis of how many donating sites are present on the ligand. Unidentate ligands means, uni means 1. Okay, uni means 1. So only the ligand whose only one donor atom is bonded to the metal atom is called a unidentate ligand. Examples, what could be examples? We have already discussed some examples like chloride, ammonia, water. There could be more. Carbonyl, cyanide. In case of cyanide, carbon will bind. Carbonyl, carbon will bind. Okay. So that's how unidentate ligands donate. They have only one donor atom which is bonded to the metal. Coming to the second category, that is didentate ligand, or we can say bidentate. It could be written in both the ways, by di or bi. Didentate or bidentate ligands are ligands which contain 2 donor atoms or ions that are bonded to the metal ion. Example 1 over here I have shown ethylene diamine. Other example, see ethylene diamine over here it is written 2 nitrogen atoms are bounded, or other example could be oxalate ion. Oxalate ion is basically COO minus COO minus. So over here this oxygen atom and this oxygen atom both will donate to the metal. So this is the figure I already have, has 2 oxygen atoms which can be binded with the metal. Four examples of this could be polydentate ligands. Polydentate ligands, we are generalizing. Unidentate ligands were those where only one donor atom is bonded to the metal. Di or bi could be the ones where 2 donating sites are present on the ligand. 2 donor atoms will be present on the ligand that will attach to the metal atom. And the tridentate could be the one where the 3 donor atoms could be attached. So similarly, polydentates, now we are generalizing. Polydentates are ligands where several donor atoms are present in a single ligand and the ligand is called polydentate ligand. Example could be this nitrogen attached with, I think we say it to be triene. Triene by means NH CH2 this, this, or this. This is the structure triene. Triethylene basically we can say. No, the name would be different. So basically here, this nitrogen will donate, this nitrogen will donate, this nitrogen will donate, and this nitrogen will also donate. So it is a tetra dented ligand. Okay. Four donating sites will be present. And for similarly, ethylene diamine tetraacetate. Let me show you the structure. So ethylene diamine. First, ethylene diamine. Okay. Now they are saying tetraacetate. Tetraacetate means CH2 COO minus CH2 COO minus CH2 COO minus CH2. Okay, we have already drawn the CH2 in between. So that is from, where is the eraser? We can say like this nitrogen attached to CH2, then one COO minus acetate group, CH2, no, CH2 I have already drawn over here, CH2 COO minus. So how many donating sites are present? Donating sites, if you consider, this O minus will donate, this O minus will donate, this nitrogen has a lone pair, it will donate, this nitrogen has a lone pair, it will donate, this O minus will donate, this O minus will donate. 1, 2, 3, 4, 5, 6. 6 donating sites are present. So it is a hexadentate ligand. It can bind to 2 nitrogens and 4 oxygen atoms present to a central metal ion. So it is a hexa-coordinated ligand, hexadentate ligand. Coming to the other types of ligand that are ambidentate ligand. Ambidentate ligands are the ones where ligand can ligate through two different atoms present in a single ligand. It means a ligand has A, Z, 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 Z or B. Could be anything in between. So it can coordinate from A side as well and as well as from B side. But at a time, will donate through only one. Either metal will bind through A or metal will bind through B. So such kind of ligands are called ambident ligands. Examples could be NO2, SCN. Here NO2 is can be linked through nitrogen as well as oxygen NO2. NO2 has nitrogen as an binding site or oxygen as a binding site. Similarly, SCN has nitrogen as a binding site as well as sulfur as a binding site. Sulfur has two donor atoms, no? So either sulfur can donate or either nitrogen can donate. Coming to the next category, that are chelate complexes. Chelate complexes are the ones, are the metal complexes in which there is a close ring of atoms caused by the attachment of the ligands. Or we can say that chelate complexes are formed when ligands attach to the metal in such a way that a close ring is formed. I'll show you example. Say, this they have shown NH2, CH2, NH2. Okay, ethylene diamine. One more CH2 has to be present in between. So it is basically CH2 2. Okay, so copper attached to the ethylene diamine NH2, CH2, CH2, NH2. Okay, this nitrogen will donate. Similarly, like this, NH2, NH2, and NH2. Now tell me, okay, this ethylene diamine is forming a ring. How many membered ring is this one? Count the number of ions, like count the number of atoms in that ring. One atom, two atom, three, four, five. It is forming a five-membered ring. Okay. So ligands that after ligands that form rings after attaching to the metal ion, these form chelate complexes. Chelate complexes. Other example I'll also show you. For example, oxalate, if you consider. In case of oxalate, let's suppose metal is attached to oxalate. C, when oxalate has oxygen O minus, C double bond O, C double bond O, O minus, like this. Let's suppose three molecules of oxalate are attached. O, O, and this. How many membered rings are present over here in this? One, two, three, four, five. So it is also again forming a five-membered ring. So these kind of complexes are called chelate complexes. So what we understood in today's video, we understood about coordination compounds. Coordination compounds are the one that do not dissociate in water. For example, K4FeCN6, where some ligand is present, as central atom is present, and a counter ion is present. Ligand is donating its electron to the metal via a coordinate bond, and double salts, and these do not dissociate in water. They do not dissociate in water, while in case of double salts like Mohr salt that we discussed, they, when we add water, they dissociate. Okay, but coordination compounds do not completely dissociate in water. We understood what is a coordination entity. Coordination entity is the one present in the square bracket. It is called a coordination entity. Central atom in this coordination entity will be iron. Ligands here in this example is cyanide. Ligands that donate electrons, central atom which are taking electrons from the ligand. Okay, donor atoms. It is not necessary that the ligand has only one donating atom. It could be more than one. In case of cyanide, carbon is donating. In case of oxalate, two O minus are donating. In case of ethylene diamine, two nitrogens are donating. Okay, donor atoms are that. Coordination number. Coordination number is defined as the number of donor atoms attached. Not the number of ligands, it is number of the donor atoms attached. For example, FeEN3 has a coordination number of 6 because ethylene diamine has two nitrogens donating. 2 into 3 of such ligands will form a coordination number of 6. Coordination sphere. The one inside the square bracket is called a coordination sphere. This part is called a coordination sphere. Okay, counter ions. Potassium ion present outside the coordination sphere, it is called counter ion. K4, or you can say 4K plus. This is a counter ion. Coordination polyhedron, as I told, generally coordination compounds are either octahedral, either that means it has 6 ligands attached to it, or generally it is having 4 ligands attached to it. If it is having 4 ligands, it could be tetrahedral or it could be square planar. Okay. What we understood further? We understood charge on the complex K4FeCN6. For example, what is the charge on this complex? Charge on this complex is the FeCN6. Coordination sphere is 4 minus. What is the oxidation state? We also understood how we calculate the oxidation state. X minus 6 minus 4. X is equal to plus 2. Denticity. Denticity is the number of donating sites present in the ligand. Sites present in the ligand. For example, unidentate ligands are like chloride. Unidentate ligands we understood that have only one donating sites. Donating site. Example, chloride, H2O, ammonia, etc. Only one donating site. Didentate ligands are like oxalate, ethylene diamine. Okay. Polydentate ligands are like that forms a ring that have more donating sites. Like EDTA. EDTA has 6 donating sites. EDTA, what I told you, that is ethylene diamine tetraacetate. So first you draw ethylene diamine. Now you draw tetraacetate. Tetraacetate molecule you need to draw CH2CO O minus COO minus COO minus COO minus. So it has only 6 donating sides. 1, 2, 3, 4, 5, 6. It's a polydental ligand. Ambidental ligands are ones those have uh, those will coordinate either with any of the site, either with any one site. Example, SCN could donate from nitrogen as well as from sulfur. Okay, so it behaves as an ambidental ligand. We'll further discuss another video where we'll discuss about the Werner's theory. That's good for the today's part. So see you in the next video.